Hello, and today we're going to talk a little bit about conservation of momentum. We've already looked at momentum itself. Remember that momentum is defined as this. It's a vector quantity. It's the product of the mass of an object times its velocity. And remember that we could reformulate the second law, Newton's second law, in terms of the rate change of momentum over time. Now, if you have a situation where the sum of all of the external forces acting on an object is equal to 0, well then you can't have any change in momentum either. And when you have that situation, well, then you have conservation of momentum. In other words, the momentum of an object that is experiencing no net external force at one moment is equal to its momentum at some other time, so P sub final here, as long as there continues to be no net external force. Now, this is not very earth-shaking stuff, really. I mean, because, well, we can state it in these terms. We can call it momentum. We can say there's external forces all summing to 0. And we've certainly looked at objects where the sum of the external forces on those objects is 0. But for a single object, this isn't really telling us much extra, right? So for a single object, it's pretty simple, okay? Where if you have something and it's moving along at some velocity, and this is, say, the initial case, and you wait some time and then you look at it again, well, if its momentum is conserved, then it's going to be moving the same direction, and it's going to have the same mass, and it's going to have the same velocity so that it has the same momentum. It's kind of like restating Newton's first law, I suppose. Okay, but beyond that, it's not a particularly useful tool, just sort of restating something we already knew in terms of momentum. However, if you take a system of two objects, like I've written down here in clip art form, and you imagine a ice dancing pair here, and they're about to do one of those things where they push off of one another, and then they're going to glide for some time, and then do a bunch of tricks or something like that. Whatever. Okay, what we're going to look at is this being the initial state, where they're just getting ready to push off of one another. And then we're going to look at the final state just after they come out of contact with one another. Now we know that thanks to Newton's third law, let me grab, let's see which color, blue's good, that the force from skater number 1, so the lady here on the left, on this guy, is exactly equal in magnitude but opposite in direction to the force that he exerts on her. Doesn't matter who's doing the pushing here, right? The third law says that those forces are always going to be the same, okay? Same in magnitude, opposite in direction. Now, what does that tell us about each of their momentums? Well, it tells us that if they feel, if this is F and this is negative F, well, her momentum, right, this lady here, okay, she's going to feel a force to the left. That's going to give her acceleration to the left, and that's going to change her velocity to the left, and so that's going to change her momentum. And the same kind of logic applies with the guy over here on the right. However, if we consider them to be a system together, and we've done this before in the context of, like, I don't know, two blocks stacked on one another, or a car towing a truck, or something along those lines, right? We've had a couple of examples where we used a clever selection of the system of objects to simplify our calculations when we were doing force sums. Well, here it's going to be even more important in that if we select the system of objects to be both of these ice dancers together, well, then the net change to their momentum is going to be 0. And so if we do this, if we consider them both together, then their momentum must be conserved, at least for the moment where they're kind of pushing off of one another. After that, I suppose over time, friction from the ice and things like that will be external forces changing their momentums. But, okay, in sort of predicting their immediate motion as a result of these pushes, conservation of momentum can be a tool for us. Now, I've just sort of said, oh, well, their momentum, sum of their momentum, is going to be the same as it was before, okay? And of course, their momentum total before, as they're pushing off, right, is 0, right? They haven't had a chance to accelerate, so there's no velocity here. They're just pushing off one another. And I'm claiming that even though each of them individually changes their momentum, together the system does not. How does that work? Well, take a look at it, okay? We're going to use what we know about impulse, actually. So we know that the change in momentum, the impulse, delivered to, say, the first person, is going to be the average force, okay, that's exerted on them, times delta t, right, in the simplest model for impulse. And we know that this force that is being exerted on her is exactly the same as this force that's being exerted on him on the right. And we know that they're in contact for the same amount of time, right? It's not like one of them could be in contact for 1 second and the other one only in contact for a half second. That doesn't make any sense, right? They're clearly touching one another, and then when they stop touching one another, that's it, right? That's the end of the period of time. So these two things have to be equal as well. And so the change in momentum here and the change in momentum here are going to be exactly the same. The only difference is the sign, right, of these forces. Remember, they're equal and opposite in direction. So these force averages here, yes, they're the same in magnitude, but one will have a negative sign associated with it and one will not. And so if you sum up the changes in their momenta, you're going to get 0 because they're exactly the same magnitude, but off by a sign. Right? Clever. So what happens here? Well, let's set it up. So what this allows us to do is, if we know any 3 of these quantities, so mass is pretty easy to measure, so we might know both of their masses. And let's say that we observe the velocity of this ice skater to be, 5 meters per second. And we want to know, what's this? Okay, let's give them some masses. Let's say he is quite hefty and she is not. And that means, okay, that also I just wanted a factor of 2 between them because it makes the calculation a little easier. And if we're considering this sort of as they're pushing away, so their initial momentum is 0 because they have not yet accelerated. And then a moment after they are no longer contacting one another, so they're no longer accelerating each other away from the other, we set up our conservation of momentum. Their initial momentum is just 0. And so their final momentum must also equal 0 in total. So first there's going to be a term associated with her. That's going to be mv1. And a term associated with him, mv2, m2v2. She has a magnitude of 5 meters per second. If we set up a coordinate system wherein to the right is positive and thus to the left is negative, well then we will have 0 equals m1 v1, and stick a minus sign out in front of that because she's moving to the left, and m2 v2, we know that he's going to be moving to the right. There's no other way for for these two things to cancel out to 0 unless he is. And so we can solve for v2 by moving this term to the other side and dividing both sides by mass of the male ice skater here. Okay, so if we plug all this in, we get 50 times 5 divided by 100, and that gives us 50 times 5 is 250, divided by 100 is 2.5 meters per second. Now notice, we didn't have to know anything about the size of those forces here, right? This is a different kind of problem solving than you had when we were doing sums of forces. Okay, all we know is those have to be equal and opposite, but we don't really care what they are because we're seeing sort of their effect in the velocities that they have as they move away from one another. And just by observing things that are easy to observe, so the velocities of these two objects and their masses, we can predict any one of the bunch of quantities that we have in those equations, okay, based on conservation of momentum. So, one last thing. I did mention this earlier, but if we played the tape, if we fast forward it a little bit here, right, obviously there's a little bit of friction between their ice skates and the ground. If they're moving very quickly, then there's drag on them from the air. So over time, we would expect there to be some amount of external force acting on each of them. And that means that this condition that's necessary for momentum to be conserved would no longer be met. So yes, this kind of physics for this kind of situation is perfect for predicting his sort of initial velocity as he moves away, but is not so good about predicting what happens next. For that, we'd have to know something maybe about that frictional force. We could figure out how much he's decelerating, and then we could figure out how his velocity changes. We have other tools for that kind of thing. But this new tool is a nice one. So next time we'll take a look at a few other things. We'll introduce collisions and maybe an example, and I'll see you then.